Hey guys, so somebody asked me about acid-base and acid-base conjugates. So whenever we have a reaction, when we start on our reactant side, we're going to have to identify what is our acid and what is our base. And we use our Bronsted-Lowry definitions to identify those. And so a hydrogen has to donate into solution a hydrogen ion. And a base is going to accept a hydrogen ion, or it could donate a hydroxide, which will have the same effect because these two will react to form a molecule of water. On the product side, now we're going to have two new species, and one will be the conjugate acid, and one will be the conjugate base. And the conjugate just means it's on the product side. So we're still looking at those same definitions for acid and base. This one would still be able to donate a hydrogen ion to solution. And this one would still accept a hydrogen ion, or it would donate a hydroxide. So let's look at a specific example. Let's say we have hydrochloric acid reacts with, let's use sodium hydroxide. And what is it going to create? So I can identify easily here that this one is the acid because it has a hydrogen at the beginning. This is my base because it has a hydroxide. So this is my acid and this is my base. What happens is this is going to give up the hydrogen and it will become Cl minus. So when HCl dissociates as an acid, its conjugate base, I'm just going to abbreviate that C base, its conjugate base is going to be the chloride anion. And so when the acid dissociates, the anion is going to be the conjugate base. Now, when sodium hydroxide dissociates, it's going to create a sodium ion, and this coming over to here, you guessed it, this is going to be the conjugate. And it has to, by definition, be the conjugate acid. And we've created, in effect, a molecule of water. And this is actually where this is not the conjugate acid. This is just going to be a counterion. This will be our conjugate acid because it has to be able to donate a hydrogen ion into solution. And this one would need to be able to accept a hydrogen ion in solution. So this is your conjugate acid. So let's look at another pair. Let's do something not quite as simple. Let's use ammonia, NH3, is reacting with, let's use acetic acid. And you may see it written like this, H3O2, or you may see it CH3COOH. This is the ionizable hydrogen on acetic acid, which is the same as this one here. These are covalently bonded to the carbon. So, since this has acid in the name, we're pretty sure this is going to be our acid. And since this is going to be the acid, this has to be our base because it has to accept that hydrogen ion. And so when we do that, this hydrogen will now be associated with the NH3, which would make it NH4 with a plus charge. And we will also have CH3COO minus. So now we're not making a molecule of water. We are making, however, two ions. Both are soluble in water. And this one, if we define that an acid is something that can donate a hydrogen ion into solution, it's clear that this one could donate a hydrogen. So this is our conjugate acid because it can donate a hydrogen ion into solution. This one, since it's negative, could accept a hydrogen ion, and so this is going to be our conjugate base. Again, you're just defining here using that same definition for Bronsted-Lowry acids and bases. I hope that helps.